I am SP Gupta, working as an assistant professor in the Department of Mechanical Engineering, IIMT College of Engineering, Greater Noida. I am going to take a lecture on topic fin. Before today, I will cover the following topic: uh, fin. What is fin? Application of fin, types of fin, thermal analysis of fin, and performance of fin. Before I start the topic fin, let us take an example. This is transformer. If we talk about the transformer has the coolant oil for the cooling purpose, and in the transformer there is the continuous conversion of electrical energy into heat energy. This heat energy will continuously generated, and due to this there will be the continuous accumulation of heat in the coolant oil, due to which the temperature of coolant oil may increase above the critical temperature of oil, or may increase above the self-ignition temperature of oil. If we talk about the electronic circuit is also continuously convert the electrical energy into heat energy, and when due to that continuous conversion of heat, there will be the continuous accumulation of heat. Due to this, the temperature of the electronic circuit may increase above the critical temperature at which the electronic circuit stop working. If we talk about the IC engine which is used in the bikes, then there will be the in IC engine there will be the conversion of chemical energy of fuel into heat energy, and due to continuous conversion of chemical energy into heat energy, there will be the continuous accumulation of heat inside the combustion chamber. Due to this, the temperature of combustion chamber may increase above the critical temperature, at which the expansion of piston may be take place. If we talk about the small capacity reciprocating compressor, during the compression stroke, there will be the continuous generation of heat, due to which there will be the continuous accumulation of heat inside that uh, compressor cylinder. Due to this, the temperature of uh, compressor cylinder may be increased above its working temperature. In all that four example, we see that when that system has to work per perfectly, the system has to transfer the heat from a system to the surrounding continuously, and this will be basically happen by the fin. Fin is what? Fin is basically the device which is used to increase the rate of heat transfer from the system surface to the surrounding, and this will be possible by the mode of convection only. And mode of convection is basically depends upon the Newton's law of cooling. As per Newton's law of cooling, Q convection is equal to HA into delta T, where delta T is said to be the temperature of the hot surface minus the temperature of surrounding fluids, where A is said to be the effective contact area between surface and surrounding fluid. H is said to be the heat transfer coefficient or convective heat transfer coefficient for the surrounding. If we have to increase the rate of heat transfer by the mode of convection, then what we have to do, we have, and that can be possible by three ways. And this will be possible, number one, by increasing the temperature difference. That means by increasing the value of Ts minus T infinitive, we can increase the rate of heat transfer by the convection, that is from surface of the hot body to the surrounding fluids. Number two, it will be increases by increasing the heat transfer coefficient H by changing the surrounding fluids. And third one is this will be also increased by increasing the effective contact area between surface and surrounding fluid, that is A. but for some cases it is very difficult. Mm, for some cases, we cannot change the value of h and delta t because this will be fixed by the surrounding condition. That means this is the fix for surrounding condition. Ts is the surface temperature, and T infinite is that is the surrounding temperature. This will be fixed by the surrounding condition. H is depend upon the surrounding atmosphere. That means for that for this some cases we cannot change uh, or we cannot increase the heat transfer by convection by changing the value of h and delta t because that two parameters are fixed by the surrounding condition. In that case, only we have only one option by increasing the value of a. By increasing the value of a, we can change the we can increase the rate of heat transfer. Okay, and this will be happen by the help of fin. Basically, fin is the device which is basically used to increase the rate of heat transfer by increasing the effective contact area. That means by using the fin we can increase the rate of heat transfer. uh, we can increase the effective contact area between surface and surrounding fluid, and due to this the rate of heat transfer by convection will be increased. That means fin is the extended surface on a hot surface which is basically used to increase the rate of heat transfer by increasing the effective contact area between surface and surrounding fluids. Next is the application of fin. If we talk about the application of fin, there are the n number of application of fin. Number one, air cooled IC engine. If we talk about the air cooled IC engine like bike's engine, in that case, uh, we are using the fin for the cooling surface, cooling purpose. Refrigerator condenser tubes in refrigeration, electric transformer, reciprocating small scale reciprocating air compressor, semiconductor device, and automobile radiator. This is the some applications of fins. Next, the types of fin. There are the different types of fin we are using. First one is the longitudinal fin. That means this is the longitudinal means there are the two types. One is said to be the straight and tapered fin, and second one is what, straight and uniform fin. Next, second one is what, radial fin. Third one is fin, and next one is what, annular fin. This is the example of that is the straight and uniform cross-sectional fin. This will be the straight but not uniform. This will be the tapered fin. This is the example of annular fin. This is fin, and this one is said to be the radial fin. Next one is the analysis of heat flow through the fin. Uh, this in this, let us suppose during the analysis of fin, what we have to do, we have to take some assumptions, uh, and in that, that number one is what, one dimensional heat conduction, and that should be along the length of the fin. The heat conduction is one dimensional, and that should be along the length of the fin only. The flow of heat should be steady state, and this is the along the length of the fin. And third one is there should not be any internal heat generation within the fin. The heat transfer coefficient should be in uniform over the entire surface of the fin. That means over the entire surface of the fin, the heat transfer coefficient, the value of small h should be uniform. That should not be changed. And the material should be homogeneous and isotropic. The temperature at any cross section of a fin is uniform. That means at any value of x, the temperature of that section will be uniform. Okay, that means the temperature is only the function of x. It is not the function of time. It is only the function of at any value of x. Let us suppose this will be the fin. and this is the x, that at x, any value of x, that is x, the temperature at that x, that will be uniform over the entire cross section at that x. If we take the this section, that is x1, at that x1 the temperature will be uniform over the entire cross section at that, at x is equal to x1. That means t is the function of x only, it is not the function of time. Okay. Next one is the thermal contact resistance is negligible, and the last one is what, the heat transfer by the radiation is neglected. This is the this is the 8 assumptions which is which we have to take for the calculation of analysis of heat flow through the fin. Heat flow through a rectangular fin. Let us suppose this is the rectangular fin. This surface is basically said to be the base surface from which we have to increase the rate of heat transfer by using the fin. This is the this is said to be the fin. This is the single fin. If there are n number of fin, then then what we have to do, first we have to calculate the heat transfer rate by a single fin. Then by multiply the number of fin, we can calculate the total heat transfer rate from n number of fin. That is why first we have to calculate the heat transfer rate from the single fin. After that, by the multiplication of n, we can easily get the total heat transfer rate by n number of fin. Let us suppose this will be the fin, the base temperature. That means the base temperature of fin, that is T naught. The surrounding temperature, this is said to be the TA, surrounding temperature is TA, and the surrounding heat transfer coefficient is equal to HA. Let us suppose the area of the A, that is the cross sectional area. That means this is the cross sectional area. Okay, this will be the K, that is the thermal conductivity of fin material, that is the perimeter of fin. That means this 3, and let us suppose uh, if we are at the base, and when we move from base toward the length of the fin, then we find that the temperature of fin is gradually decreases. That means the temperature of that fin is gradually decreases once we move outward from the base of the fin. Okay, that means due to this, if we have to calculate the heat transfer rate from surface to surrounding, that Q is equal to HA into delta T, where delta T is what? Where delta T is the temperature of surface minus temperature of surrounding. Then but here we see the temperature of surface is gradually decreased. That means gradually change. That is why delta T is not uniform at all the value of x are at entire surface of the fin. That is why what we have to do, we have to find the value of surface temperature at every value of x. That means x1, x2, x3, at every value of x, what we have to do, we have to calculate the uh, temperature at x1, x2, or x1. After that, we find the value of delta T1, delta T2, delta T3, and then we have to calculate the value of Q1, Q2, Q3, and the by summation of all Q1, Q2, and Qn, we can get the heat transfer rate from the surface. And this is very difficult task. Then what we have to do? First, we have to take the element in that fin. So let us suppose elemental cross section area of thickness dx. This will be the elemental cross section area, and the thickness of that element, that means the thickness of this element will be dx, and it is at a distance of x from the base of the fin. That means it is at a distance of base. This will be the base, then the distance of that element from that base is equal to x. Okay, let us suppose that capital T is the surface temperature of that element. Okay, let let us take that element outside and do the analysis of that element. Okay, and this is the element, this element, this is the element, and we see that element um, uh, at left side from the left side of the element there will be the another layer, and right side is also there will be the another layer of that fin. That means the heat will be in from in this side, and the heat will be out from this side, and that upper surface, this surface, and this one surface, this surface, that is the uh, surface area of the element, surface area of the element that is exposed to the surrounding. That means the heat will be enter from left side of the element, and this by the mode of conduction. Then we can say that that this is the qx, and this is the rate of heat in at x is at a distance of x. That means this is at a distance of x. Similarly, the rate of coming out from the element at a distance of x and plus dx. Okay, this is the qx plus dx. And the next one is what the surrounding fluid is contact with the surface area of that element. That is why there will be the heat transfer from that elemental surface area to the surrounding fluid by the mode of convection. That means there are the three heat transfer takes place. Okay, if we do the energy balance equation for that elemental area, then what we will get from the energy balance equation, the total rate of heat in is equal to rate of heat out. That means qx is equal to qx plus dx plus q convection. That means the heat conducted into element at x is equal to heat conducted out from element at x plus dx plus heat conducted out by convection between x and x plus dx. That means this is equal to qx is equal to q convection plus qx plus dx. Okay, that is the equation. Q conduction into the element at x is equal to q conducted out from element at x plus dx plus q convected out between x and x plus dx. Okay, then that means this qx is equal to qx plus dx plus q convection. This will be the equation number one. Then what we have to do, first we have to individually find the value of qx, qx plus dx, and q convection. By qx is equal to heat convected into element at x. That means that is the heat conduction, and it will be based on the Fourier's law of conduction, and this will be equal to minus kac dt by dx. Similarly, qx plus dx, this will be equal to heat conducted out from element at x plus dx, and this will be equal to qx plus del qx upon del x into dx. Okay, this will be the value of qx. Next one is what? Q convection. Q convection is equal to what? Q convection is equal to heat transfer coefficient h. Okay, q convection is equal to heat transfer coefficient h into the surface area. Here the elemental surface area h into this will be equal to, this is equal to elemental surface area, and this is equal to elemental surface area, and that can be written as p into dx. That means perimeter into the thickness, perimeter into thickness. This will be the elemental surface area where the surrounding fluid are comes into contact, and that capital T is the surface temperature at that element minus surrounding temperature. Okay, then putting the value of qx plus dx and q convection in equation number one, then we can get the value of qx, and qx is cancel out. Okay, then minus del qx upon del x dx, that minus ha t minus ta, this will be equal to 0. Here the value of a is what? Here the value of a is said to be the elemental surface area, and this will be equal to p into dx. Then that can be written as here the value of qx is equal to this one. The value of qx is equal to this one, that is equal to minus ksc dt by dx minus HA T minus TA, that will be equal to 0. That is equal to H. Yes, this A is equal to what? This A is equal to P into dx. This is P into dx, where P is the perimeter and dx is the thickness of that element. Okay, into T minus T infinite. This will be, that means this dx and dx will be cancelled. Then by simplify this equation, we can get the d square t upon dx square minus hp upon kac t minus ta is equal to 0. Let us assume t minus that will be the temperature difference, and this will be equal to theta, and hp upon kac, that will be equal to m square. So m square is equal to hp upon kac. By integrating this equation with respect to x, then dt by dx is equal to d theta by dx, because this will be the constant and theta is the function of t. Then by differentiating the d theta by dx is equal to dt by dx. Similarly, d square theta upon dx square is equal to d square t upon dx square. That means we again differentiate this equation with respect to x, then we will get this equation. Putting the value of d square t upon dx square and hp upon ks in this equation, then we can get d square theta upon dx square minus m square into theta, and this will be equal to 0. This is looking like a second order differential equation. This is the said to be the second order differential equation, and we all know that the second order for this equation, the solution equations are theta is equal to c1 e ki power mx plus c2 e ki power minus mx. Okay, this will be the equation number 3. Then where c1 and c2 is said to be the integration constant, and that can be calculated by using the boundary condition. Then what we have to do, this integration constant can be calculated by using the boundary conditions. Okay, this is said to be the integration constant and can be found by using the boundary condition. Then found for boundary condition, we have to find the cases how much cases can possible in case of the fin. Then in case of the fin, there are the 3 cases can be possible. Okay, number 1, when the fin length is infinite long. That means when the length of the fin is infinite, but means first we assume the length of fin is infinite. Second one is what? The fin length is finite, but tip is insulated. The length is not finite. The second one, in second, the length of fin is not infinite, it is finite, but the fin tip is insulated. There are no any heat interaction from the tip of the fin. Third one is what? When the fin length is finite long and tip is not insulated. Tip is not insulated means the tip of the fin is exposed to the surrounding for the convection purpose. That means the heat will transfer from fin tip to the surrounding by the mode of convection. Then what we have to do, we have to find the boundary condition for every cases, and by the help of that boundary condition, we can get the value of c1 and c2, and by putting the value of that c1 and c2 in equation number 3, we can easily get the temperature distribution equation for every cases. Okay, then for what is the task? First we have to find uh, what is the possible boundary condition, and we have to find minimum 2 boundary condition, because we have 2 unknown. That is why we have to generate minimum 2 equation for the calculation of c1 and c2. This is the number 1. When the case number 1, when the fin length is infinite long. That means in case number 1, let us assume in case number 1 the length of the fin is infinite long. Okay, then what should be the boundary condition? In case of the infinite long fin, this is the base where the fin is origin. That is at that the x is equal to 0, and this is said to be the x is equal to infinite. X is equal to infinite means not the here it is the not meaning of the length of the fin is 200, 300 and 400 meters. That means the value of x is infinite means the length of the fin at which the surface temperature of fin is equal to the surrounding temperature, then that length is basically said to be the infinite length. I am repeating again. At the length of the fin at which the surface temperature of the fin is equal to surrounding temperature, then that length is assumed to be infinite long. That means we can say at x is equal to infinite, the surface temperature of fin is equal to surrounding temperature Ta. At x is equal to 0, where we are at the base of the fin. That means we feel the temperature of base, that is T naught. There are the two boundary condition. First one is what? At x is equal to 0, the temperature at x is equal to 0, where we are at the base. That means we feel the temperature of base, that is T is equal to 0. And theta, we assume theta is equal to T minus T naught, sorry, T minus Ta. In that case, if the value, put the value of T naught, then theta is equal to theta naught, and when we put the value of T is equal to T naught, that means theta is equal to T naught, and that will be equal to T naught. Here the T is equal to T naught. Second boundary condition is what? At x is equal to infinite. At x is equal to infinite means that is the length at which the surface temperature of fin is equal to surrounding temperature. That means T is equal to Ta. When we know the theta is equal to what? Theta is equal to T minus Ta. We assume it Ta. Okay. When at x is equal to infinite, T is equal to Ta. When we put the value of T is equal to Ta, then Ta cancel. That means theta is equal to 0. That means at x is equal to infinite, T is equal to Ta, and theta is equal to 0. By these two boundary condition, we can easily get the value of C1 and C2. Okay. Then this will be C1 is equal to 0 and C2 is equal to theta naught. This by putting the value of C1 and C2 in equation number 3. Equation number 3 are what? Theta is equal to what? Theta is equal to here. Theta is equal to what? C1 e की power mx plus C2 e की power minus mx. And then by putting the value of C1 and C2, we can easily get the value of theta is equal to C1 is equal to 0 and C2 is equal to theta naught. Then this will be equal to theta is equal to theta naught e की power minus mx. Okay, this is C1 is equal to 0, C2 is equal to theta naught. Here C1 is equal to 0 and C2 is equal to theta naught. Then theta is equal to theta naught e की power minus mx. This term is equal to 0. Then this can be written as theta by theta naught is equal to e की power minus mx. This is the temperature distribution equation for the case number 1. That is when the fin length is infinite long. Okay, and then theta is equal to what? Theta is equal to T minus Ta, and theta naught is equal to T naught minus Ta. By putting the value of theta and theta naught, we can get the another temperature distribution equation for case number 1. Next one is the heat transfer rate through fin. Uh, Let us assume This is the fin. Okay. Then the heat transfer rate is steady state. In that case, uh, if we have to calculate the rate of heat transfer by the mode of convection, then what we have to do? First, we have to find the value of T at every value of x. Okay, that means at the value of x1, x2, x3, x4, x5, x6, and xn. What we have to do? First, we have to find the value of T, and then we have to calculate the value of q1, q2, q3, q3, q4, q5, and qn by using q is equal to ha into delta T. And then by the summation of q1 to qn, we can easily get the value of total heat transfer from the surface. And this is very difficult task. Then what we have to do, we have to find the value of q1, q2, q3, and qn. This is very difficult. Then here what we have to do, we have to use the steady state heat conduction problem. Okay, in that case, we know a steady state heat flow process, the rate of heat in at the base of fin. This is the fin. The rate of heat in at the base of the fin, this will be equal to the rate of heat out by the mode of convection from the surface of the fin. That means the rate of heat transfer from the fin, that will be equal to the rate of heat conducted into the fin at base and at x is equal to 0. That means uh, the, uh, the rate of heat conducted into the fin at x is equal to 0, that will be equal to the total rate of heat transfer from the surface of the fin. That means it is very easy to calculate the rate of heat conduction at x is equal to 0, and it is very difficult to calculate the rate of heat transfer by the fin by using Q convection. Okay, then by using this we can easily calculate. That means, and because the rate of heat conduction is basically depends upon Fourier's law of conduction. Okay, that means Q fin is equal to minus KAC dt by dx at x is equal to 0. Here, the dt by dx should be at x is equal to 0. It should not be at another place because we have to calculate the heat conduction at x is equal to 0. Okay, that is why we have to put dt by dx at x is equal to 0. When we put dt by dx at x is equal to 0, then it will give the rate of heat conduction at x is equal to 0. Clear? Then by using the uh, temperature distribution equation for case number 1, we can easily get the value of dt by dx. Dt by dx can be written as d theta by dx. Okay, then minus kac d theta by dx at x is equal to 0. Then by putting the value of d theta by dx at x is equal to 0, and this can be calculated by the help of temperature distribution equation, which already explained in last slide. Okay, then theta is equal to theta naught e की power minus mx. Okay, by differentiating with respect to x, d theta by dx is equal to minus m theta naught e की power minus mx. This is the d theta by dx. We have to calculate the d theta by dx at x is equal to 0. Clear? Then d theta by dx at x is equal to 0. That means this x is equal to 0. That is the 0. Then this will be equal to minus m d theta. Okay, putting the value of dt by ds at x is equal to 0, putting the value of d theta by ds at x is equal to 0, and this will be equal to minus m into d theta. That means minus kac and minus minus theta theta naught into m. Okay, this minus and minus is equal to plus. That means this will be equal to ka minus and minus will be cancelled, and we know m square is equal to hp upon kac. That means m is equal to what? hp under root hp by kac. That means by putting the value of m, that is under root hp upon kac, this kac and kac will cancel, then this will be equal to under root hp kac into d theta, into theta naught, and theta naught is equal to t naught minus ta. That is equal to q fin is equal to under root hp into kac multiplied by t naught minus t infinite. This is the heat transfer through fin when the fin length is infinite long. Okay, clear? Next case is what? Next one is the case number 2, when the fin length is finite long and tip of fin is insulated. That means this will be the in that is the second case. Then what we have to do? First we have to find the minimum two boundary condition. Here again at x is equal to 0. Here the length, that is the length of the finite, it is not infinite. That means the length of the fin, this will be equal to, let us assume that is the capital L. At x is equal to 0, we are at the base, and at base, that is why we feel the temperature of base, that is T naught. That means the first boundary condition is what? At x is equal to 0, T is equal to T naught, and theta is equal to theta naught. Okay, uh, at that is the x is equal to L. X is equal to L means when we are at a tip of the fin, and at the tip of the fin, here the tip is insulated. Because the tip is insulated, that is why there are no any heat interaction, that is there are no heat transfer by the mode of conduction, and that is why the temperature gradient at tip is equal to 0. dt by dx at x is equal to L, that will be equal to 0. dt by dx at x is equal to L, that will be equal to 0. Why it is? Because the tip is insulated. That means there are no any heat transfer across the insulation by the mode of conduction, and this will be only possible when the temperature gradient is equal to 0. That means at x is equal to L, dt by dx is equal to 0, or d theta by dx is equal to 0. By putting these two boundary condition in equation number 3, this is the equation number 3, then we can easily get the value of C1 and C2. This is the C1 and this will be the C2. By then putting the value of C1 and C2 in equation number 3, this is again the equation number 3, then we can get the temperature distribution equation for the case number 2, that is the fin length is finite long and tip of the fin is insulated. That means theta is equal to theta naught is equal to cos hyperbolic m bracket में L minus x divided by cos hyperbolic ml. Here theta, that can be written as theta by theta naught is equal to this one, and next we know theta is equal to t minus ta and theta naught is equal to t naught minus ta, then that can be written as theta naught. This is the three simple expression for the temperature distribution equation when the length of fin is finite long and tip is insulated. Clear? This is the, similarly we can find the heat transfer rate through the fin by from the fin. Okay, in that case, and this similarly in that case also the heat transfer from the fin is equal to rate of heat conducted into fin at x is equal to 0. That means minus KAC dt by dx at x is equal to 0. Clear? The rate of heat conduction from the fin, that will be equal to the rate of heat conducted into fin at base x is equal to 0. Similarly, similarly as case number 1. Here again we have to calculate the dt by dx at x is equal to 0, but this should be calculated from the temperature distribution for case number 2. It should not be the temperature distribution for case number 1. Okay, then we have to calculate the value of dt by dx at x is equal to 0 from temperature distribution equation for case number 2. Okay, this will be equal to, this is theta, this is the case number 2 of this is the temperature distribution equation for the case number 2. By differentiating with respect to x, we can easily get the value of d theta by dx. Okay, d theta by dx at x is equal to 0, simple, put the x is equal to 0, and then this is equal to minus m theta sine hyperbolic ml divided by cos hyperbolic ml, and sine by cos is equal to tan hyperbolic ml. Then putting the value of d theta by dx at x is equal to 0 in this equation, then we can easily get the heat transfer rate by the fin. Clear? That will be equal to HKAC m theta m into theta tan hyperbolic ml. Okay, m is equal to under root hp upon kac. That means under root hp upon kac. KAC and KAC cancel, then this can be written as HP under root HP into KAC d theta tan hyperbolic ml. Okay, and d theta is equal to what? T naught minus TA. Then Q fin is equal to under root HP KAC T naught minus TA tan hyperbolic ml. This is the heat transfer rate through fin for the case number 2, that is when the fin is finite long and tip is insulated. Clear? There are no any heat interaction from the tip. That is only for the case number 2. Similarly, we can calculate by the help of case number 3. That is the case number 3 when the fin length is finite long and tip is not insulated. That means in that case tip is not insulated and there will be the heat interaction from tip of the fin to the surrounding by the mode of convection. Similarly, in that case, at base at x is equal to 0, here again the length of the fin is given. This is equal to capital L. Okay, at x is equal to 0. At x is equal to 0, where we are? We are at the base. That is why we feel the temperature of base. That means at x is equal to 0, T is equal to T naught. Okay, and theta is equal to theta naught. But at x is equal to L, at x is equal to L, where we are? We are at the base. We are at the, sorry, we are at the tip, and the tip is not insulated. That means there will be the heat transfer from the tip surface to the surrounding by the mode of conduction. That is why we can say at the tip the rate of heat conduction is equal to rate of heat convection. That means at the tip at x is equal to L, the heat conducted at tip at x is equal to L is equal to heat convected from tip to the surrounding at x is equal to L. By putting the value of this, that is minus h into this is depends upon the this depends upon the Fourier's law of conduction, and this is depend upon the Newton's law of cooling. Then by using the Fourier's law of conduction equation and Newton's law of cooling, we can easily get the boundary condition. Okay, this is the boundary condition. By using these two boundary condition, we can easily get the value of C1 and this is the value of C2. By putting the value of by putting that two boundary condition equation number 3, we can easily get the value of C2 and C1. Then by putting the value of C1 and C2 in equation number 3, we can easily get the temperature distribution equation for case number 3. Okay, this is the temperature distribution equation for the case number 3. This is the equation number 3. By putting the value of C1 and C2 in that equation, we can easily get that equation. Okay, similarly we can get the heat transfer rate for the case number 1, and similar concept we have to use here also. What? The rate of the heat transfer by from the fin, that will be equal to the rate of heat conducted into fin at x is equal to 0. Similarly here, by using this equation, what we have to do? We have to find d theta by dx at x is equal to what? 0. Okay, then what we have to do? We have to differentiate that temperature distribution equation with respect to x, and then we can easily get the value of d theta by dx at x is equal to 0. Then by putting that this we can easily get the heat transfer rate for case number 3. Clear? Then the heat transfer rate similar for case number 3 is equal to heat conducted into at x is equal to 0. It depend upon the Fourier's law of conduction. That means this is the Fourier's law of conduction. Then what we have to do? We have to find the d theta by dx for from temperature distribution equation for case number 3. I am repeating again. We have to calculate or we have to find the value of d theta by dx at x is equal to 0 from temperature distribution equation of case number 3. That is when the fin length is finite long and tip is not insulated. Okay, clear? Then we can easily get the temperature distribution, sorry, heat transfer rate through the fin. This is the equation of q fin for the case number 3. This is the 3 possible case. I'm again repeating that there are the three possible cases for the fin. Number one, when the fin length is infinite long. Okay. Number two, when the fin length is finite long but tip is insulated. And number three, when the fin length is finite long and the tip is not insulated. That means there are the heat transfer by the mode of convection from tip surface to the surrounding. Clear? Next one is performance of fin. Okay. The performance of, if we talk about the performance of fin, then this is basically depends upon two parameter. One is fin efficiency and second one is fin effectiveness. By calculating these two parameter, we can easily get the performance of the fin. Clear? This is the fin. If we talk about fin efficiency, what is fin efficiency? Fin efficiency means the heat transfer from the fin with respect to the maximum possible heat transfer. That means it is defined as the ratio of actual heat transfer to maximum possible heat transfer through the fin. Clear? That means this is defined as the ratio of actual heat transfer rate through fin to maximum possible heat transfer rate through the fin. That means Q fin fin efficiency, this will be equal to Q fin divided by Q maximum. Here Q fin is equal to the heat transfer rate through fin, which already we have calculated for case number 1, case number 2 and case number 3. But here first we have to find what should be the value of Q maximum. Okay, so let us suppose this is the fin base surface where we are fitted with that fin. Okay, the base temperature is T naught. Clear? Then what should be the maximum possibility that the heat transfer rate will be maximum from the surface? We say I say you that the temperature when we move outward from the base of the fin to on, then the temperature of fin is gradually decreases. Okay, that is why the value of T minus T naught, sorry, T minus Ta, that will also be gradually decreases because the value of T is gradually decreases. That is why the rate of heat transfer rate is again once move outward, then the temperature, then the heat transfer rate will decreases. Why it is decreases? Because the value of T minus Ta is decreases. Then the heat transfer rate will be maximum is only when the entire surface has the same temperature, and that will be equal to T naught. If the fin surface is equal to T naught, in that case that is the maximum possibility of heat transfer rate from the fin. Clear? That means if we have to calculate the value of heat transfer rate from the fin, uh, then what? Then Q is equal to what? Q is equal to H into AE. AE is what? Effective contact area and multiplied by delta T. Delta T, what is delta T? Delta T is equal to T naught minus Ta. That means when T delta T is equal to T naught minus Ta, that means when the entire surface temperature is equal and that will be equal to T naught, that is the case of maximum heat transfer rate. Okay, that means Q maximum is equal to H into AE multiplied by T naught minus Ta. A is the what? Effective contact area. That means surface area, and surface area is equal to, this is AE or AS. This is equal to PAS. This one is the AS. Then AS is equal to P into L. Perimeter into length of the fin. If we multiply the perimeter with the length of the fin, then we can easily get the effective contact area of the fin. That is the surface area of that fin. Clear? This that means the for infinite long fin we already know Q fin is equal to under root HP KAC T naught minus Ta, and Q maximum is equal to what? H into PL. That means H into PL multiplied by T naught minus Ta. H into PL. This is equal to H into PL T naught minus Ta. Putting the value of Q fin and Q maximum, we can easily get the efficiency of fin. Okay, this is the efficiency of fin. T naught and T naught will be cancelled. this will be cancelled, and PL, that P is cancelled, this and H is cancelled. That means under root 1 upon, this is 1 upon L into under root KAC upon HP. HP upon KAC is equal to M. That means KAC upon HP under root is equal to what? 1 upon M. This will be equal to efficiency of fin. This will be equal to 1 upon M dot L. This is the value of efficiency, and it is only for when the fin length is infinite long. We can similarly calculate when the fin is finite long. Okay, in case of finite long, the value of q fin is equal to what? Under root HPKAC T naught minus TA multiplied by 10 hyperbolic ml. Okay, q maximum is same for all three cases. Clear? Then efficiency of fin is equal to 1 upon ml into 10 hyperbolic ml. This will be equal to this will be for the case number 2. Similarly, we can easily get the efficiency of fin for case number 3. Okay, next one is what? Fin effectiveness. Fin effectiveness means uh, what will be the comparison of heat transfer rate when we are using fin and when we are not using fin. That means that will be the comparison between two heat transfer rate when we are using fin and when we are not using fin. That means this is the case. Okay, this will be the case when we are using fin. When we remove the fin, that means when we are using fin, this all the area is exposed area, and that area is responsible for the heat transfer. That will be the huge area. Okay, and when we are not using fin, then this will be the area, this large area will be a small area. In other words, we can say when we are not using fin, this will be the small area, and that small area will be converted into that large area when we are using fin. That means this is the area, effective area, which is exposed to the surrounding when we are, and this is the cross section area of the fin when we are not using the fin. Okay, when we use uh, the fin at that a cross section area, then that small area will be converted into that large area, and this is said to be the AS, surface area of the fin, and this will be equal to what? P into L. Okay, perimeter into length of the fin. Clear? Clear? Okay, then in that case, this is the ratio of heat transfer rate with the fin divided by without fin when we are using fin and when we are not using fin. That ratio of these two will give the effectiveness of the fin. That means it is defined as the ratio of heat transfer rate with the fin. That means when we are using the fin. With the fin means which we have calculated for the case number 1, case number 2, and case number 3. This is said to be the with fin means q fin, or without fin means that is the that means without fin. If we talk about without fin, that means q is equal to what? Ha into delta t. Ha here, a is exposed area, so what? Hac, clear, multiplied by here temperature is T naught, because this is the base temperature, and minus surrounding temperature is Ta. This is the heat transfer rate when we are not using the fin, and q fin is already we have calculated for the case number 1, 2, and 3. Clear? Then the performance of the fin ki baat, then effectiveness, it is defined as the ratio of heat transfer rate with fin to heat transfer rate without fin. That means effectiveness is equal to q fin with fin divided by q without fin. That means for infinite long fin, we have to consider the case. Let us consider the case number 1. The length of the fin is infinite long. Clear hai? In that case, q fin is equal to under root HPKAC T naught minus TA, already calculated for case number 1, and the value of q without fin, that is equal to HAC T naught minus TA, already explained for this expression in last slide, where AC that. Okay, then the ratio of these two give the effectiveness. That means T naught and T naught will be cancelled, AC cancel, and H cancel. That means this will be equal to Kp upon HAC. This is the effectiveness of the fin. Okay, clear? Thank you.